Hello everyone, welcome to Explore Physics. We are going to discuss about the very interesting and vital topic electricity. The movement of water molecules in a particular direction forms water current. The movement of air molecules in a direction forms air current. Similarly, the flow of electric charge or electrons through a conductor constitutes electric current. The valence electrons in the conductor are in random movement. That is why just in a copper or aluminum wire there will be no flow of current. A cell or a battery placed in proper order provides the flow of charges or electric current through a conductor. A switch makes a conducting link between the cell and the bulb to form continuous and closed path for the flow of electric current. And if the switch is off, that is the circuit is broken, the current stops flowing and the bulb does not glow. Such a continuous and closed path of an electric current is called an electric circuit. Electric current is expressed as the amount of charge flowing through a particular area in unit time, or it can also be expressed as the rate of flow of electric charges. If a net charge Q flows across any cross-section of a conductor in time t, then the current I through the cross-section is given by the equation I equals Q upon T. The SI unit of electric charge is coulomb. Just imagine 1 coulomb contains 6 into 10 to the power 18 electrons, and 1 electron possesses a charge of a negative of 1.6 into 10 to the power minus 19 coulomb of charge, and the SI unit of current is ampere. The unit of current is named after a French physicist and a mathematician by name André Ampère. He made important contributions to the theory of electricity and magnetism in the 19th century. Well, 1 ampere is the flow of 1 coulomb of charge per second. Mathematically, 1 ampere equals 1 coulomb upon 1 second. Small quantities of current are expressed in terms of milliamperes and microamperes. 1 milliampere equals 10 to the power minus 3 ampere, and 1 microampere equals 10 to the power minus 6 ampere. An instrument called ammeter measures electric current in a circuit. It is always connected in series in the circuit through which the current is to be measured. This is a typical electric circuit consisting of a cell, switch, bulb and ammeter, all connected in series. This is a schematic diagram of an electric circuit comprising of a battery consisting of 2 cells, a bulb, ammeter, plug key, all connected in series. And the direction of current is indicated conventionally from positive end of the battery to the negative end. Now we are going to discuss about how the charges flow inside a solid conductor or a wire. The atoms in the solid are packed together with very little spacing between them. But the electrons are able to travel through a perfect solid crystal smoothly and easily as if in a vacuum. When a steady current flows through a conductor, the electrons in it move with a certain average drift speed of the order of just 1 millimeter per second for a typical copper wire. Well then, how does a bulb light up as soon as we switch on the current? It is not possible that a current starts only when an electron moved from one terminal of the electric supply physically reaches the other terminal through the bulb, because the physical drift of the electron is a very slow process. It is quite controversial that the electricity travels almost the speed of light, but the electrons are very slow, even slower than the gliding of a snail. If there is a race between the snail and the electron, it's sure the snail would win the race, as it is observed that the snail moves 38 times more faster than the electron in a conductor. Then one way to visualize the movement of the electron in a conductor may be taken as the transfer of energy of an electron at one end of the terminal to the electron at the other end. Thus the bulb lights up as soon as we switch on the current. Well, now we are going to discuss about what makes the electric charge to flow through the conductor. To understand the concept more better, let's consider the analogy of the flow of water. Here you observe the flow of water through the pipe from the tank to the tap. We make use of the water pump to fill the water in the tank, overcoming the gravitational force, and maintain the pressure difference for the continuous flow of water in the tap. In the similar manner, we make use of an electron pump, that is a cell or a battery, to maintain the pressure difference for the continuous flow of current through the wire. Thus the charges flow from high potential to low potential. This is the conventional indication. But we are now sure that the high potential is the negative end and the low potential is the positive end, and the flow of charges is from negative end to the positive end. The energy provided by the cell for the flow of electric charges through it is called electromotive force. Well, in the conductor, the electrons as such keep moving in a haphazard manner, since they experience the force of attraction by the positively charged atoms as well as the repulsive force by the negatively charged electrons in the electric field within the conductor. Hence the electron moves from some point, say infinity, to another point in the conductor by itself. This amount of work done by a charged particle to move itself from infinity to other point is called as electric potential. But once the conductor is connected to a battery or a cell, the electrons align themselves and tend to move in a particular direction. At the anode of a cell or a battery, the negative charges repel the electrons in the conductor and creates an electric pressure at that point, and sets the charges in motion in the conductor, thus allowing the charges to flow from negative terminal to the positive terminal of a cell or a battery. Electric pressure, or simply potential difference between 2 points in an electric circuit, is defined as the work done to move a unit charge from one point to the other. Mathematically, potential difference equals work done upon charge, and symbolically V equals W upon Q. The SI unit of potential difference is volt. Potential difference is also referred to as voltage. The unit of potential difference is named after an Italian physicist, chemist and pioneer of electricity and power, Alessandro Volta. He is credited as the inventor of the electrical battery and the discoverer of methane. Well, 1 volt is defined as the potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. Mathematically, 1 volt equals 1 joule upon 1 coulomb, and symbolically 1 volt equals 1 joule per coulomb. The potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. you have understood the concept. We'll explore more in the forthcoming videos. Thank you.